6 transformations, or 2.5 presents to 6 transformations, but we only look at 5 of those. So we do have only one left, which is, any questions, ladies? Danielle, please. Kendall, please. So horizontal, stretching, shrinking. This is the only one that it's not, let me say that it's not going to be exactly what you expect. All the other ones, I think they're straightforward. But this one is not straightforward. Also, we do not have a base function to illustrate it with. Okay, there is no base function from the 7 ones that we went through or studied that I can illustrate this with. So we will be illustrated with a graph. And we're going to copy a graph from the book, and we're going to illustrate what happens. But before that, I have to explain what they mean and what happens here. What needs to be change when we encounter a horizontal stretching or horizontal shrinking. So every horizontal transformation is a transformation in X, right? And any transformation up and down or on the y-axis must be a transformation in y. Okay, so obviously this will be a transformation in X because it's horizontal. So we're only talking about change in X. Okay. Next thing, let's suppose we have f of x, which is x cubed. We know this graph. We're going to come back again to this graph in chapter 3. So we remember it. I know I look silly, but I just want to explain something. So this is x cubed, correct? Mm-hmm. Right? This is x cubed. Doesn't have a max or a min. It just crosses the x-axis very slowly, not straightforward. You'll understand in chapter 3 what that means. So it goes slowly at the origin and goes up. Now I would like to create another function. But this time, the function is f, the same function, but I'm replacing x by twice x. So I replace x by twice x. And let's see what happens. Now, please plug in 2x in this function and tell me what you get. Or what should I write as the first step? Yes, but let's write the first step for everyone to see, and then we'll simplify it.
2x, right? 2x.
Very good. And now I have to raise 2 to the third power, which is, and I have to raise x to the third power, which is good. So now, forget about this. Forget about where it came from. So let's try again. So this is x cubed. What does 8x cubed do? From the previous transformations. Not connected to what we're talking about. It is connected, but forget about what we're talking right now. Careful. Careful. It has an 8 in front of x cubed. What transformation is this now? Is it a change in x? No. So this was x cubed. Where does 8x cubed go? Is it plus? If it's plus, then I go up. If it's minus, then I go down. But it's not plus and it's not minus. It's multiplied. Exactly. It stretches it by a factor of 8. Is that clear? Right? Exactly. Right? When we multiply x cubed by 8, we stretch it by a factor of 8, correct? Now let's think of how we started this. We changed x into twice x, and this is what happened. What am I doing to x? One more time. This is the original. This is f of twice x. What am I doing to x? Stretching it or shrinking it? Yes. This is exactly opposite. So when we replace x by twice x, we horizontally shrink the graph.
Wait, I thought it stretched it by a factor of 8.
That's vertical.
Oh.
So that's why I went back to what we knew from before.
Okay.
So 8x cubed is this.
Right.
But horizontally, it does not mean stretching. It means shrinking.
makes it wider.
No. Shrinking it.
Wider would be like going.
Exactly. Yes. So this is the only transformation that you will probably not expect the result to be this. So when we change x by twice or 2, or we transform x into 2x, we horizontally shrink the graph. But what will happen now if I want 1/3 x plugged in this function? What will you say? You will say 1/3 x everything cubed, and you will also say 1/27 x cubed. Now forget for a moment where this came from. This is x cubed. What does 1/27 in front of x cubed do? Yes. So when we change x into 1/3 x, x into 1/3 x means we horizontally stretch the graph.
So fraction equals stretch.
Yes, it's exactly opposite from the y. So if I have 2x cubed, I do this.
So if it's a
If I have
horizontal-
1/2 x cubed, then I do this.
So if you're trying to get both, it's the opposite. If horizontal is stretch, vertical will be shrink.
But I wouldn't remember it like that, but if you want to, it works. Okay, very good. So let's look at an application.
Is
And
there a vertical stretch?
I'm sorry?
Is there a vertical stretch?
No. When we change x into 1/3 x, you can say it triggers something like that, but I cannot use the base function for this. What we illustrate this transformation, that's why I left it at the end. What we illustrate this transformation with base functions are trig functions, like sine, cosine, tangent, cotangent. This transformation works beautifully with that, with those functions. But here I don't really have a base function to work with, because this is the opposite transformation, which is either horizontal stretching or horizontal shrinking. But I cannot illustrate just one. So I illustrate it so that it's embedded in our system now, that when we change x into twice x, it's not this, but it's the opposite. And when we change x into 1/3 x, it's not this, but the opposite. That's all I wanted to illustrate with this. So now let's look at a problem. Let's say 50, yes, 50. And you can choose another if you want. 50 on page 296. We will have to copy the graph. It's a very easy graph to work with. Okay, so -4, comma, -2, then -2, 0, then 0, 2, and then 2, 2, and 4, 0. So this is the graph of function f. Notice is obviously what type of function that we discussed before, and we even graphed something like this. Very good. The piecewise defined function defined in 3 pieces. Very good, awesome. So we're asked to find in 50, we're asked to graph.
I'm sorry, I am lost. I'm on page 296, but I don't see where 50 is.
Oh.
Okay, thank you.
Sorry about that. So it's g of x. So this is g of x. And thank you. I always copy from something. But this time I copied the correct graph, but I didn't give it the correct page. Sorry about that. So we have 1/2 f of twice x. Okay. So what is the first transformation we have to perform on graph G in order to graph 1/2 f of twice x? Remember the order of operations. So first I have to graph f of twice x. And this is indeed f. It doesn't say, but it has to. Oh, yeah, it does say. Of course, it's f. And we want to graph g. Good. So what does f of twice x, what does it do to the graph of f? by a factor of 1/2. Correct. Because we changed x into twice x, it's not this, it's the opposite, so we have to shrink it. So each and every x coordinate for the corresponding points, not for all of them because it will take a day. So for this point, I will divide its x by 2. For this point, I will divide its x by 2. For this point, I will divide its x by 2. For this point by 2, and this point by 2. So for the first point, please divide x by 2. Right here. The y value does not change. For this x value, please divide it by 2. For this x value, for the x value of this point, divided by 2. For this point, its x value, please divide it by 2. And for this x value, for this point, its x coordinate divided by 2. This is the graph of f of twice x. Okay, now the next step is 1/2 in front. So what do I do now? So let's put it in writing. Horizontal shrinking by a factor of 1/2. What does this do to this graph? Careful. Vertical shrinking. Vertical shrinking by a factor of, no change there, still 1/2. Only the horizontal stretching or shrinking are backwards, if you want, sort of. Good. So now for 1, 2, 3, 4, 5 important points, I will divide their height or their y value by 1/2. So this is at -2. It doesn't, the x does not change now. So this is a -2. Where does it go? Let me use blue. This point has the y value at 0. Where does it go when I divide 0 by 1/2 or multiply by 1/2? I divide by 2. 0. This y value is at 2. I divide it by 2. Where does it go? 1. This y value is at 2. I divide by 2. Where does it go? And finally, this is at the y value of 0. Where does it go? This is the final graph, which is g of x. 1/2 f of x, f of twice x. Any questions on this? Yes?
How do you know if it's like, because like for the horizontal stretching and shrinking, like for shrinking, like it's in 2x, and for stretching, it's like 1/3
Yes.
and above.
So that's why I didn't want to combine, and I left this one by itself. So if I change y with a 2 in front, it's a vertical stretching. If I change y with a 1/2 in front, it's a vertical shrinking.
Okay.
If I change x into twice x, it's a horizontal shrinking. If I change x into 1/3 x, it's a horizontal stretching.
So it's basically if it's in the group, it does one thing. If it's outside the group.
Exactly. That's what I said. If it's a change in x, you'll think in those in certain terms. If it's a change in y, in different terms. We always separated that from day one with transformations. I always ask you, what is it? Is it transformation in x or in y? So we know what to do. Okay? Do you think we need another example? Or very good. So let's choose another. Anything that changes x into 1/3 x, 1/2 x, or 2x, or something like that. Do I get to choose? 49. We won 49. Very good. 49 it is. It's on the same. So 49, same page. It's on the same function, but I have to copy it from scratch. So the same graph, -4, -2, 2, 2, 4. So this is function f. What is the first transformation we have to apply to f?
Horizontal stretch.
Very good. Very good. So it's a horizontal stretch by a factor of 2. Awesome. So it's a transformation in x. So this point is at -4. Where will it go? At -8. Good. This point is at -2. Where will it go? This point is at x equals 0. Where will it go? This point is at x equals 2. Where will it go? This one is at 4. Where will it go? So this is the graph of f of 1/2 x. When we change x into 1/2 x, we stretch the graph by a factor of 2. All y coordinates stay the same, but the x coordinate changes. It doubles. The final step here is twice the function from part 1. What does this do? Is it a change or a transformation in x or in y? If it's in y, it's regular. What you would normally expect to do. What do I expect to do? It's multiplied. It's not 2 plus. If it's 2 plus, then I shift the graph up 2 units. But it's twice. So now the y value. The y value here is at -2. Where will it go? At -4. This y value is at 0. Where will it go? This y value is at 2. Where will it go? This y value is at, this y value is at 2. And this y value is at 0. So here it is. This is the final graph, g of x. So this is a vertical stretching by a factor of 2. Normal. No changes there.
And the other one was a vertical shrink.
This is, no, when we change x, it has to be horizontal.
Yeah, but like the first one we did.
This one was a vertical shrinking by a factor of 1/2. Exactly what's in front. No change. But the f of twice x was a horizontal shrinking by a factor of 1/2. Only when we change x into twice x or x into 1/3 x, it happens to, the transformation is something that we would not normally expect. Everything else should be straightforward. Okay, that's all I said I had to say about 2.5. And we would like to continue with 2.6, combinations of functions and function composition. I call this algebra of functions. What does algebra of functions or algebra means? It means addition, subtraction, multiplication, and division of functions. So if we are given two functions f and g, we can add, subtract, multiply, or divide them to get new functions. So these are 4 different ways. 4 different ways of finding new functions or creating new functions. There is a 5th one, which is called function composition. So there are 5 different ways of creating new functions if I'm given at least 2. Okay. So let's start with, this entire thing should be a review, but I will go through it. This was presented in a previous class, but that's okay. So let's say we are given f of x. I'm going to say x squared plus 1, and g of x, let's say 2x squared minus 3x minus 2. If someone asks you to find a function named f plus g of x, what does that say to you? Common sense says that you are really asked to do what? F of x plus g of x, indeed. I'm going to go ahead and just replace them. So then I have x squared plus 1 plus 2x squared minus 3x minus 2. And of course, I have to combine like terms like I would normally do. So then I get 3x squared minus 3x minus 1. This is a totally new function, was determined by adding the given functions. The name is self-explanatory, because if I come to you and say, hey, create function t of x, you should say, you haven't told me how. But if I ask you find the function f plus g of x, you cannot ask anything. You know what it means, right? It means adding those two functions. Same thing for f minus g. This must be f of x minus g of x. Have to be very careful because I have to distribute the negative sign or negative 1 to all terms in g. So this is x squared plus 1 minus 2x squared plus 3x plus 2. When I subtract function g, I have to distribute negative 1 to all terms because it's a polynomial function. Otherwise, it would have been something else. So negative x squared plus 3x plus 3. This is a new function. It was determined by subtracting the given functions. Of course, fg, which by definition means f of x times g of x. All I have to do is just write them side by side and distribute. This is not good enough by simply writing them like that. I have to distribute, combine like terms, presented in descending order. So 2x to the 4th minus 3x to the 3rd minus 2x squared plus 2x squared minus 3x and minus 2. Any questions? Please stop me if you have questions. I know you're my best, but still. Any? Yes. So 2x to the 4th, negative 3x cubed, negative 2x squared, positive 2x squared, minus 3x, and minus 2. So it happens that these two go away. The degree of this polynomial is very good. Now, I want to come back for a second, and can anyone tell us the domain of f and the domain of g? I know you would probably wonder, what did she ask that from the beginning? So what would you say about the domain of f, Amanda? Can anyone tell us why these two functions are defined on all their numbers? What type of functions are they? Yes, but under the big umbrella of, it's called polynomial. Polynomial functions, linear, quadratic, cubic, they're all defined everywhere. Very good. So what do you think about the sum? Where will the sum be defined? It's still a polynomial. It's still quadratic. Exactly the same domain. It's polynomial. Correct. What about this one? Same thing. What about this one? Very good. They're all defined on all their numbers. I will explain something in a minute. But now I would like to look at f over g. That's the last function from the algebra of functions. Can anyone give us the definition for this? Yes, but I have to write f of x over g of x. That's a definition, and now I replace them. X squared plus 1 over 2x squared minus 3x minus 2. However, I did not say this before for the sum, difference, and product, but here I'm going to put an if, and I'm going to wait for you to tell me if what.
G of x.
It can be negative, but it cannot be 0. Correct. Very good. Only if g of x is not 0. Indeed. So I have 2x squared minus 3x minus 2 set equal to 0 because I need to find the domain of this function. We have what type of equation to solve? Quadratic. We know 4 methods. Yes, if factoring it takes long, then definitely the quadratic formula. I will not take square roots, it's not ready. I will not complete the square ever unless I have to. And the other two options are factoring or quadratic formula. Which one would you like to apply? Quadratic formula will take less time.
Usually I would factor in 2.
Yes, let me show you. So this is the product. The product is this when the leading coefficient is not 1. This is -4. And the sum of these same numbers is -3. So we want two numbers, one negative and one positive, because the product is negative, such that the product is -1 and the sum is -3. So what do I have for sure? -4 and +1. But then I have to change the equation into 2x squared minus 4x plus x minus 2 equals 0. And I was not, since this triggered my memory, I was expecting everyone to do that extra credit. So I'm not sure what happened. I saw something all over the place on that factoring extra credit from the test. So we should talk about it. Okay, so now what do I do? Because I have 4 terms. And 4 terms means grouping. We are still solving a quadratic equation. I can't have 4 solutions from here. I can only have 2. Very good. So then, I didn't say. What do we factor out? And what is left in parentheses?
X minus 2.
So then we have an x minus 2 here, right? 2x times x and 2x times -2. So some of you got confused. You did not write the correct factor here, and you couldn't factor. So be very careful. If you don't get the same, that's why I cover it, to make a point and just trigger your memory. If you don't get the same factor, I can't continue. So there was that polynomial equation with degree 3. So you got here x minus 2 and here 5x minus 3. That's not possible. You can't continue. So then what is left in front?
1.
So then x minus 2 times 2x plus 1 equals 0. Well, obviously, we don't want this to happen. So I don't want this to be 0, which means x not equal and x not equal.
-1, huh?
Perfect. Do you agree with 2 and -1/2? Do we agree with 2 and -1/2? So now I would like us to determine the domain. The domain of the ratio. So here's the ratio. We know that the denominator cannot be 0. We know that this function is not defined when x is -1/2 and when x is 2, because the denominator will be 0. So what is the domain then? There is infinitely many real numbers between -1/2 and 2.
So there's 2 unions?
Yes?
So it's -1/2 and 2.
Very good.
And then 2.
Very good. Always remember, between -1/2 and 2, we will not live as long. to name all those numbers. It will be probably a million lifetimes. Okay, now let's talk about what is called common domain. And then we'll look at a problem from the book that you can choose. Okay, so let's suppose I have two functions. One function that is this. I'm going to put some numbers in here. I'm going to say -2 and 5. And another function that is this. Of course, this is 0, and I'm going to say that this is 10. So this is function g. The orange one is g, and the brown one is f. And I want to ask you to find f plus g of 8. Before you look at the graph, you will say that's easy, right? What will it equal to? Exactly the same procedure we just did, but this time is 8 instead of x. So what will I write? Exact same procedure. We're asked to find the function, thank you, the function that is evaluated at 8 of f plus g. So it must be f of 8 plus g of 8. We're not distributing or anything like that. We know that. So now I look at the graphs. How much is f of 8? Awesome. Undefined. So if I want to ask you to evaluate the sum, difference, product, or ratio, where can I ask you to evaluate? For what x values I can ask you to evaluate it?
Greater than 0.
And less than? Where they both exist. Where do both exist?
0 to 5.
Right. So if you cross this with a horizontal, with a vertical line, you will see they both exist only between 0 and 5. Outside of 0 and 5, I can't ask you. You're not going to be able to give me a number. So this is what we call the common domain. If there is no common domain, so common domain for these two functions is 0, 5. If I ask you f over g at 3, you will be able to find it. If I ask you fg of 0, you will be able to find it. But for example, if I ask you f minus g at -2, you will say, sorry, I can't. Why? Because f is defined at -2, but g is not. So all the first two work, this one does not. Why? Because the value I picked is not in the common domain. So these are possible. This, undefined. So algebra functions works only if the functions you give me have a common domain. If they don't have a common domain, what's the use of it? They don't exist. So let's choose another pair of functions. On page 310, from 31 through 50. Okay, I will pick 40. In 40, we have f of x equals the square root of x, and we have g of x, which is x minus 5. We are asked to determine all those functions, the sum, difference, product, and ratio. But first I have to find the domain of each, because I need to identify the common domain. So what is the domain of this function? We graphed it. We have the graph in our head. We graphed it in transformations. We know the picture of the graph, and we can say immediately that the domain is.
Oh, constant numbers.
Say it again.
Oh, constant numbers.
We remember the graph, correct? Good. So what is the domain of G? And what type of function is it? Right.
Oh.
It's polynomial. It's a linear function. I can plug in anything I can dream of and beyond. So domain is very good. Now I need to find the common domain, which will always be, for any pair of functions, will be the domain of f plus g, the domain of f minus g, and the domain of fg. Always. I'm not sure about the domain of the ratio. I have to investigate further. But the common domain that we come up with now, we don't have to write it again. It will be the domain of the sum, difference, and product, for sure. Okay, so can anyone give us the common domain of these two functions? In other words, where can I ask you to evaluate the sum, difference, product, or ratio? Of course. Do you all agree with 0 to infinity? Perfect. So now let's create the sum, then the difference, then the product, and then the ratio, and find the domain of the ratio. We should write the definition first, which means f of x plus g of x. We should copy the square root of x plus x minus 5. No one can combine like terms. No one can do anything here. When we determine the difference, we write the definition so we don't forget what we are trying to do. And this is the square root of x minus x plus 5 because we have to distribute the negative sign inside x minus 5. No one can simplify. This is it. Fg, by definition, is f of x multiplied by g of x, which is the square root of x times x minus 5. But we don't like to write anything behind the square root, so I recommend reverse them. Multiplication is commutative and associative, so 2 times 3 is 3 times 2. No one can further simplify this. Nothing else is needed here. Now we finally, there is a lot of writing here, but it's just writing, nothing sophisticated. So this is f of x over g of x. This is the square root of x over x minus 5, and I have no choice but put if in here. If what? And we've been doing this from day one, right? When we solved what type of equations? We had to write restrictions like this. What type of equations are these with x in the denominator? Thank you, Eric. Very good. So if what?
If x doesn't equal 5.
Awesome. So now I would like to present the domain of the ratio because the problem is asking us to find all domains. So can anyone give us a domain of the ratio?
Oh, sorry.
We would be tempted to write negative infinity to 5, union 5 to infinity, correct? Okay, so let me make a note. So that's note. From the common domain, we must exclude 5. Why? Because we have those functions that have to have common domain. So the common domain, we cannot create this if they're not defined on the common domain. From the common domain, we have to exclude 5. So what will that domain be then? From the common domain, that's where these functions exist. These two functions at the same time, they exist at the same time on the common domain.
Bracket 0 to
Right.
5, parenthesis, and
Yes.
union, parenthesis 5 to infinity.
Perfect. So I have to go back before I draw a conclusion here. I have to look where the two functions exist at the same time. Because if I made the mistake to write negative infinity to infinity without 5, you're going to see the function does not exist at the left-hand side of 0. So that's function composition. For example, I like to look at problem 28 before we move on, where we are given a function g of x, the square root of x minus 3 over x minus 6. You could say that this is a function that is determined how? As a ratio of two functions. Function from the top and function from the bottom. Right? However, here we are only asked to find the domain. Okay. What do I have to write in order to find the domain? One thing is for certain. You will say what?
X minus 6.
Very good. As we know, we've done that so many times. Absolutely. The denominator cannot be 0. Now let's look at this. We already have the picture of the graph in our heads. We know the square root of x, and where is the square root of x minus 3 going? Right. So what is the domain of the top?
X is greater than 3.
Exactly. So what I recommend here, always write x minus 3 greater than or equal to 0. This is for this. So I have two restrictions, x greater than or equal to 3, but not 6. So let's look at the real line if this gets confusing. So 3 to infinity is this. This is 3 to infinity. And we do not want 6 in there. We don't want 6. So what is the domain of G then?
Would be 3 to 5.
3,
6 and
right, 6 to 3.
Is that clear?
But if you don't want 6, why would it be 2, 6?
Because it'd
It's
be bracket
parentheses.
if it
Parentheses means it doesn't include.
Okay.
That's what it says in mathematical terms. Everything from 3 to infinity without 6. If I make an error and put a bracket somewhere, this 6 or that 6, then I messed up the answer. That would be incorrect. Very good. So let's look at the fifth type. Okay. So let's say we have these functions now. F of x equals x minus 1. Any questions for me? Any questions? Please ask. You may see something I didn't say or I didn't do. Any questions? Okay, and let's say g of x equals negative 2x squared plus 1. And let's look at three bubbles. And let's say I have x here. And I decide to apply g to it. What do I get? G of x, of course. This becomes a number now. And then let's suppose I would like to apply f to it. When I apply f to this number, what do I get? That's it. This is function composition. This is function composition. Which function we applied first to x? Good. So it's f comp g. G is the inner function. F is the outer. Why is f the outer? Because first we choose to apply g to x. And then at the end, we applied f to g of x. So this is the definition of f comp g. So first of all, let's write it the way we read it. F comp g. Or the composite of f and g. F comp, this is a circle. This is not addition, multiplication, subtraction, or division. A totally new method of creating new functions. So it's f comp g. And the definition is exactly what you gave me right here. You said f of g of x. Now, please tell me, what would the definition be if I were to ask you to find f comp f? What will you say? That's it. Thank you very much. What if now we want g comp f of x?
G of f of x.
Thank you, Eric. Perfect. Okay, but now let's see how we do this. I'm going to copy the functions one more time. One remark that I would like you to understand is a big note here. For function composition, there is no discussion of common domain. There is no need. There is no need of common domain. They don't have to have a common domain to create a function composition. Can we run into problems? Yes. Will I ask you to find the domain of a function composition in this class? No. But let me just explain what the problem could be. So for function composition, there is no need of the common domain. The functions don't have to have common domain. So forget about this function for a moment. You look at g, this is x values, this is the y values. How do I call this set? Where I pick values of x for function g. It has a name. We used it 10 times today already. Exactly. Very good. Thank you, William. This is domain of g. Perfect. What does this represent for g? Exactly. Thank you. Range for g. Now, what does this bubble or set represent for f? Exactly. So this is the domain. Thank you. Domain of f. So what could go wrong? Here's what can go wrong. But I'm not asking you to determine this. Only in my pre-calculus class we did it. So I can bring a number here that is 5. But this function is not defined at 5. I will not be able to get here. So the range of g and the domain of f have to work well together. If they don't, the chain is broken. You don't need to do this. This is just a for your information, okay? But just remember, we do not need to find the common domain for this. There is no point. The domain of the function composition does not depend on them, the functions, having the common domain or not. Okay, so let's say we are asked to find f comp g. And we have to write the definition, which is f of g of x. I have to start with the inner function. The inner function, do not cross it out like that. I'm just trying to make a point. So this is f of negative 2x squared plus 1. And now I have to go back to f and see what is f asking me to do. F says f of whatever is whatever minus 1. Can anyone dictate? What do I have to write?
Negative 2x squared plus 1 minus 1.
Whatever minus 1. Whatever minus 1. These two go away, so this is negative 2x squared. So this is the first function composition we created. It's f comp g. We replace the g by what it equals to, and then we asked ourselves, what does f want? Well, f wants g of x minus 1, and that's what we did. Now, let's say we want to determine g comp f. The definition is g of f of x. I don't cross it out like that. I'm just making a point. That's our starting point. So I know I have to evaluate g at x minus 1. So I have to look at g, and g says g of whatever is -2 times whatever squared plus 1. So what do I write?
-2 times x minus 1 squared plus 1.
Okay, so now I have to simplify it. When I square a binomial, what do I get?
Trinomial.
Very good, thank you.
Minus 2x plus 1.
Very good, thank you, Tamara. Now I can distribute -2 and combine like terms. Any questions? Any questions? Okay, so I'm not going to ask you to determine the function composition